We have talked about the least squares regression line, which is a line that is fitted to the data and describes the relationship between an explanatory and a response variable. With that, we have this concept of a residual. A residual is the difference between the observed value and the predicted value. Residuals are useful because in most cases, we're not going to have a line that will pass exactly through all of the points in a scatter plot. So the residuals help us to understand what the difference is between what our least squares regression line is predicting and those actual results that we are getting. So in order to calculate a residual, we have to take our observed value minus our predicted value. Our observed value is y, and our predicted is y hat. So y minus y hat will give us our residual. So now let's apply the things that we've been looking at and that to example number 7. Example number 7, the plot below shows how many hours 10 students studied for Mr. Roberg's test and what score they received. The least squares regression line for the data below is y hat is equal to 66.7 plus 8.4x. Part A says to rewrite this equation in context. When we rewrite our equation in context, essentially what we are doing is we are getting rid of the variables so that we can have a better understanding of what is taking place. In this example, our y value is the score, or our response value is the score on the test. We could rewrite this as the predicted score is equal to 66.7 plus 8.4 times our explanatory variable. And our explanatory variable is the number of hours studied. Part B says to graph the least squares regression line on the plot below. Just like we would in Algebra 1. 66.7 is our y-intercept. I'm going to go to approximately where 66.7 would be. So from there, I'm going to use my slope and go up 8.4 and over 1, and we're going to be at about 75.1. So just about where this other point is. And then I'm going to use a line to connect my points. And there is my least squares regression line. For part C, it says to interpret the slope in context. What does our slope mean in this situation? Our slope is telling us that for every 1 hour that we increase in studying, our score, or our predicted score, is going to go up by 8.4 points. We could write for each hour increase in studying, we predict on average an 8.4 increase in the score. Part D says to interpret the y-intercept in context. Our y-intercept, or where we are starting, that is what happens when our x value, or when our explanatory variable, is 0. So if we don't study at all, our predicted score is a 66.7. If we do not study, it is predicted that we will score 66.7. Part E, what score would you predict someone who studied 2.5 hours would get? We are going to use our equation to predict this. So our y hat is our predicted score. It's equal to 66.7 plus 8.4 times the number of hours. In this case, it is 2.5 hours. And when we multiply and add together, we end up with y hat being 87.7. A person who studies for 2.5 hours is predicted to earn a score of 87.7. That might not necessarily occur. And what actually happened here, a person that studied for 2 hours scored a 90. But based on our least squares regression line, that is what we are predicting. Part F, what is a predicted score for a person who studies 4 hours? Again, we're just going to have to substitute 4 into our equation. And we end up with a score of 100.3. A person that studies for 4 hours is predicted to have a score of 100.3. Part G says to calculate the residual for the person who studied 4 hours. Our residual is our observed value minus our predicted value, or y minus y hat. Looking at our table, looking at our graph, we can see here that a person that studied 4 hours earned a score of 100. Our predicted value is 100. And then, not our predicted value, our actual value is 100, and our predicted value is 100.3. Therefore, our residual is negative 0.3. Since our residual is negative, that tells us that the actual score is lower than the predicted score. Now, in a lot of situations, there are points where our least squares regression line no longer is going to hold for our situation. For example, here, if we are talking about somebody who studied for 7 hours, this is going to predict a very high score, but we cannot get over 100 points or 100% on this test. Thus, our predictions are limited to a certain span amount of time, usually the span where our data is located. Part H here said, what was the actual score for a student who studied for 2 hours and had a residual of 1.4? We are looking for y. So first, we need to find our predicted score for 2 hours. So y hat is equal to 66.7 plus 8.4 times 2. And we find out that our predicted score is 83.5. If we study for 2 hours, we predict that we would earn 83.5 points. We want to know the actual score, though, if our residual is 1.4. Therefore, Our actual score minus 83.5 must be equivalent to 1.4. So we're going to add 83.5 to both sides. And we end up with our actual score of 84.9. Some correlation and regression wisdom. So correlation and regression are powerful tools for both describing the relationship between two variables. When you use these tools, be aware of their limitations. And there are 4 areas of wisdom or caution that we use when we look at correlation and regression. The distinction between our explanatory variable and our response variable is important in regression. We don't want to mix them up. If we mix them up, our slope and our y-intercept are going to be incorrect. Correlation and regression lines describe linear relationships. We can find correlation and regression for any type of relationship, but it's not going to make sense in the context of the problem. So they only are used when we're talking about linear relationships. Correlation and least squares regression lines are not resistant. Outliers highly affect them. If there are outliers in our data, we have to take that into consideration because it's going to drastically change our correlation and our regression lines. And the last one is that association does not imply causation. Two things might be related to each other, but it doesn't mean that one thing causes the other. For example, in this graph down here, we have murder rates and the number of ice creams sold. As the murder rate goes up, our numbers of ice cream sold goes up. This does not say that an increase in murder rates causes increase in ice cream to be sold. Or we cannot say that that increase in ice cream sales causes murder rates to go up. There are other things that are lurking in the background, such as temperature, the fact that when it gets hotter out, more people are out and about, and also when it gets hotter out, more people tend to buy ice cream. So there could be some underlying factors. So even though these look like they are related, it doesn't mean that one causes the other.